Thanks for the reminder. Nice. Right, so yes, so here we are, and we are looking at a model car in a garage, and the roof of the garage looks like a fairly conventional, it's a convex shape, sort of tent shape roof. Right, so if I were to ask you what is the shape of the roof, that would be what you would most likely tell me. However, if I put a mirror behind the car, right, this is the reflection of that same roof in the mirror. Notice now it's looking different, right? On one side you have the convex shape, and on the other side the mirror reflection is giving me two sort of inverted V's, right? And then if you look at it sideways, you know, seeing that neither of them are true, that is really cut in a particular way, and depending on how you look at it, you get a different answer. In other words, perspective is going to make quite a difference. So this is what we're getting into inside of here. Optical illusions, the whole answer with the optical illusion has to do with that point of perspective. So most of the times when we speak about signals, let's think about a sinusoid, for instance. What you would think of when I tell you, okay, draw a sinusoid for me, what you would do is to draw something like that on the screen, which is the kind of thing that you would see on an oscilloscope. And if I were to ask you, what is the frequency of that signal there on the screen, what would you tell me? How would you work out that? What's the frequency of that sinusoid in the drawing there? Right, 1/6 hertz. Right, time is in seconds, so about, let's say the period looks like about 6 seconds. So the interval or the frequency is 1 over the period, so 1/6 hertz, right, which is about 0.15 something hertz. So if I draw a graph of signal frequency versus the amplitude of the signal, the peak is the peak here is 1. So if I tell you the amplitude, which is 1, right, the peak amplitude, let's use the amplitude as being the peak value is 1, and the frequency is 0.15. So if I draw this now on instead of a time versus amplitude, I draw this as frequency versus amplitude. This is what I am getting. Amplitude 1 and signal 0.15 hertz. And then if that the first one was cosine t, and I ask you what is cosine 3, sorry, the first one is cosine omega t, and I ask you what is cosine 3 omega t. This one, if the first one was a frequency of 1/6 or 0.15 about, this one is going to be 3 times that. Yeah, it's about 0.45. So plot signal frequency versus, so the line moves to here. What about this? If I add the two of them, if I add the two of them together, so I run this pass into a little summing circuit, I'm going to get this the signal coming out below here. What is the frequency of that? Just looking at it, it's kind of hard to tell, because if you want, I mean, you could look and say, okay, the big pulse repeats itself just a little over every 6 seconds. All right, but then we have some other little ones inside of here, and they're repeating themselves differently. So what exactly is the frequency of that? In other words, if you never saw if you never saw these two, and all I were to give you that and ask you what's the frequency of that signal, you can't tell me. The most you can do is to tell me that somewhere inside of there, according to the big peaks, there's something happening at every 1/6 hertz, right? But we know that in fact, this is what it is. So in other words, our perspective is a little bit different. The time perspective, looking at the time varying signal here, right, I can see that this is clearly not a sinusoid. With experience, I could figure out that maybe we have a couple of sinusoids mixing up inside of here. But it's giving me some information here. Some information, yes, I'm seeing what the amplitude looks like. I'm seeing what the envelope looks like, and the like. On the other side now, this now is telling me that that particular signal now has two frequencies in it. Right? It has a 0.15 hertz, it has a 0.45 hertz, and that both of them have amplitude 1 volt. All right. So in either case, you're given the same thing, but you're getting a totally different view of it depending on your perspective. So the time domain is giving me what the envelope looks like, so I could get an idea and I could see it. Here now, I'm actually getting, this is like an X-ray into it. This is actually telling me what that signal is. So in other words, to get all of the information, usually of signals and the behavior of things, sometimes you need to look at it from not only from the front, you have to look at it from the side, from the top, underneath, all. And putting all the information together will eventually give you what the true picture of the particular signal looks like. If you keep adding here, we could keep adding multiples of the original signal. So I could get, if I add 1 plus 3 omega plus 5 omega, I keep getting this kind of thing. And if you keep doing it, right, just like that, without any manipulation, otherwise, the average is starting to look something like this, right? It has a little peaking here and there, the change points. But if you add enough of this, so this is 1 omega plus 3 omega plus 5 omega. That's what I have here. If I add 7 plus 9 plus 11, in other words, all of the odd multiples of omega, eventually I'm going to get something looking like this. A kind of very noisy square wave, more or less looking like a square wave, right? Kind of looking like a square wave, but with some, and we saw the term yesterday, a lot of overshoot. Okay? But if you just watch the plain signal here on the screen, you can't tell how many components actually make it up. All you know is that, yeah, there's something strange inside of here. The envelope sort of looking, if we have enough harmonics, the envelope is going to look like a square wave with some added features on it. All right? So again, the point is that as engineers and the perspective and our focus in signals and systems is to get an insight. When you're given something, how much information, how much insight can I get about what that signal or system actually looks like? Now, this behavior was actually discovered by Joseph Fourier, right? Actually, his surname wasn't Fourier. He was the Baron of Fourier. That county, his surname was really Joseph. But anyway, he came up with the idea way back when that any periodic signal, and there's a key to at least a Fourier series, any periodic signal could be represented as a sum of sines and cosines. It took a long time afterwards for the mathematicians to prove it. Remember, a sine and a cosine are the same thing, except that there's a phase angle of 90 degrees or pi over 2 difference between the two of them. So he showed that sines and cosines, that you could take any periodic signal, anything, no matter what the shape was like, and you could break it down into a series of sines and cosines. And of course, they named the Fourier series representation of a signal. It was named after him. Now you can imagine doing that with paper, because he wouldn't have had any what do you call it, computers and MATLAB and all that kind of thing, and wouldn't have had even textbooks like what you have right now. He would be learning the mathematics and sitting down and doing the calculus and finding the equations of all sorts of arbitrary periodic waveforms and doing the math. Okay? And you probably didn't have much pencils and pens, so you're doing that, sorry, pencils and erasers, so you're doing that with pens. So anyway, just a little aside, he's also one that they credit with being the discoverer of the greenhouse effect. That thing that is creating all of this bizarre weather that we have around. He discovered that under certain conditions that the atmosphere can actually act like a greenhouse and not radiate the heat outwards into space, and then you get, well, what a greenhouse does, which is to keep in heat. It traps ultraviolet and keeps in. So he actually figured that one out, right? So when next you think about the Fourier series, don't only think about the maths that giving you so much trouble. Think about the fact that the person who came up with that maths also figured out that we have this thing called the greenhouse effect that we're suffering with, right? So if you put it down mathematically, and you said you did it or you're doing it already in math, so the Fourier series representation is basically given by this signal here. So any continuous time periodic signal, right? Once you have the period, in terms of something called its fundamental frequency, which is the base sort of frequency in it, that you could take the signal now and express it as a constant plus a sum of cosines and a sum of sines. All of them are multiple frequencies of the fundamental. So k is an integer, is going to run from 1 to infinity, right? A0 is when k is naught. So this is the DC value. So in other words, if the waveform or the signal, the periodic signal, has a DC value, right? And you know how that would look. If I were to draw a normal sinusoid, it looks like this. It's symmetrical, about 0 volts. But if it had a DC value on it, then what would happen? It would be looking like this, right? Where the average value, it goes plus and minus about some average value here. This is the DC value, right? So you can have both. So the Fourier series saying that regardless in general form, that any periodic signal, you could break down into a DC component, it may or may not have it, and then a sum of sines and cosines, where the frequencies are multiples of the fundamental frequency of the signal, and you put some little things in front of it, some coefficients that we call weights. So that tells you how much of each component there is. So this is called the trigonometric representation of the Fourier series. In other words, we're using normal trigonometric expansions. And if you were to expand there, what this says is that the signal is some A0 and A1 cosine omega and B1 sine omega, and then A2 cosine 2 omega and B2 sine 2 omega, and so on, right? Until you reach the end, until either the A's or the B's turn out to be zeros, or the sines and the cosines. Yes, Sadie, question? Why do we always use an increment of 1? Well, it's a think about it. I'm summing harmonics, right? Or I'm summing multiples, sorry, of, I didn't introduce the term as yet, but like when I was introducing the signals before, what I have is omega, and the next, as it turns out, the next easy multiple of that will be 2 omega, and the next easy one will be 3 omega. If I were to do it like say omega, and then the next one is 0.1 omega, and the next one 0.2 omega, it now makes the thing a lot more complicated, right? For no reason. And then it's just a mathematical convenience. So, or then somebody else might say, okay, well, why use that? Why not omega, 5 omega, 5.5 omega, 7 omega? Then at that point in time, it now becomes inconsistent. If you standardize the increments, so we are saying and remember, k is going from 1 to infinity, so it has an infinite number of integer multiples of omega inside of here. If I were to make omega vary continuously, then I can never have the summation like this, right? But you raise an interesting point, and I'll come back to it when we do the Fourier transform. All right, so don't forget it yet, all right? Don't let me dismiss it as yet. But basically, for the purpose of this is what Fourier discovered, that you could work in multiples of the fundamental, and I mean that's in terms of a series, the multiples would be the same. Just now, excuse me for 2 seconds. Yeah, the integer multiples would be the simplest sort of increments. I would, if I want to do a summation, the easiest way I could do the summation is to do integer increments. It makes it easier for me to work out, and especially if I'm working it all by hand. Yeah. But it's interesting, and the integer part, eventually, when we talk about continuous, you'll see when it will come about again, right? Put it that way. So hold on to the let me hold on to the final answer there for you. Right. So the expansion is in terms of the DC average on a set of weighted sines and cosines, which represent the amplitudes of the sines and cosines. Right? It's kind of like how your GPAs worked out. So when you're doing your GPA calculation, these are the marks, and this is the weight for your marks, depending on when you're in level 1, 2, or 3, or if it's a project. Right? So same sort of thing. A weighted, each one is given a weighting, and whether it's there or not. And right, so this was a term I didn't introduce as yet. So omega 0, they call it fundamental frequency. And then 2 omega, they call the second harmonic, 3 omega, the third harmonic, and so on. Now, if any of you all are musicians, this is going to run a little bit different from what musicians call it. Musicians would call, you have the fundamental or the tone, and the next multiple, what we would call in our signals the second harmonic, they would actually call the first, right? And the third harmonic, they call the second, because they don't count the fundamental as the first harmonic. We count the fundamental as the first harmonic. People doing music and studying music don't count the fundamental as one of the harmonics, right? The fundamental is the fundamental, right? Any multiple from there, we start counting the harmonics afterwards. All right, so sorry if I offend any of the musically inclined among you, but for signals and systems, the fundamental is the first harmonic. All right, first harmonic. So if we go on here now, right, each sine and cosine term represents a single frequency, right? This frequency is either the fundamental or the harmonics of the fundamental, and the collection of them is what we call a spectrum, right? You've heard the term before, you know it way back when you started to do your physics. Light, you pass light through a glass prism, and it broke it up, and you saw the lights coming out. The white light, if it passed through a prism, you see it coming out. You are able to distinguish just at a glance, typically the sort of seven colors. But if you look, it's actually a very continuous variation from one color to the next. It's just that we sort of concentrated on the violet, indigo, blue, green, that kind of thing. But there's a transition when you go between violet and indigo. There's a gradual, continuous move from one color to the next, and we call it a spectrum. Same thing in this. When you take up any signal and you break it up into its frequency components, that is a spectrum of the signal. And you're going to hear that term a lot in communications. You're going to hear that term a lot in our own course here, and then later on, if any of you all do signal processing with me. And you're going to hear that term when you use microprocessors, and even in power systems as well. You're going to come across the term spectrum quite a bit. Yeah. Now, one of the things that you can do is that there is a relationship between cosine and sine and the exponential function e, right? And that relationship is through what we know as Euler's relationship. So for instance, cosine x is e to the complex exponential, I should say. Cosine x is e to the jx plus e to the minus jx over 2, and sine is the other one. So you could use that now. And if I substitute for sine and cosine in the trigonometric form, I get another form of the Fourier series. And this form is what we call the exponential, the complex exponential form of the Fourier series, or sometimes called the analysis equation form of the Fourier series. Now notice a little bit of a difference here now. In the trigonometric form, k went from 1 to infinity. In the complex exponential form, k is going from minus infinity to plus infinity. So does that imply negative frequencies? Right, that's strange. It might look a little bit strange because, of course, k is the harmonic numbers. But this just happens to be because of the fact that we're now dealing with complex numbers. Remember, complex numbers come in complex conjugates, right? And if you watch the top here, if you just look at the top here and the top there, you notice that whenever you have complex numbers, normally you have a conjugate for it. So you have an a plus jb and an a minus jb. That's the situation here. So in event when you do this, all of the complex parts will cancel out, and you only get the real parts being left back, which is what we want. We're in the real world. Complex just happens to be something that arrives out or is derived out of the mathematics, but it really doesn't exist in reality. It's a mathematical creation, okay? But it allows us to make things very compact. Right, and if you look, so if the two forms are here, right, you could put the two of them there. So on top is the trigonometric form, on the bottom is the complex exponential form, and there's a relationship now between the coefficients. The complex exponential form only has one coefficient. The trigonometric form has 3, right? Of course, when k equal to 0 here, C0 is in fact 0. So we get that one out of there. And then we work out the other ones as we go along. Fair enough? That's again a different version, a different way of looking at things. And then in the complex exponential form, right, I just said k equal to 0 is our DC. K equal to plus or minus 1 is the first harmonic component, and the second harmonic, k equal to 2, third, k equal to 3. And remember this, in our terminology, the first harmonic is the fundamental. Right? So nothing new there. Now, in the complex exponential form, the particular, and we're not doing the derivation of that, but CK, how you calculate CK is by an integral. So the weight or the coefficient CK is for any signal, you take the signal and you multiply it by this thing, e to the j k omega naught t, and you're integrating over the period because it's, remember, the Fourier transform deals with periodic signals. Now this is where I was telling you that the Fourier treatment of signals and the Laplace treatment of signals start to get very similar. Notice this is very similar. It's starting to look like what we did with the Laplace transform. Remember, the Laplace transform is a x to the t e to the minus st dt. Notice that the form, right, that's the important thing, that the form is similar to the Laplace transform. So again, if you know the Laplace transform, the form of the integral, then remembering the Fourier series coefficient, the complex Fourier series coefficient, should be fairly simple now. We have the same xt, and so instead of s now, we're replacing s in this particular thing by jk omega naught, right? Notice again, we're getting closer to what we were doing in our circuits class, right? Where we said we replace s by j omega. In this case, we here, if I take the s, sorry, take away the minus sign, the same s, and at this point for the Fourier series, if I take s and replace it with jk omega naught, right? You get the coefficient inside of there. And of course, because it's periodic, you have to integrate over the period of the signal. Yeah? Fair enough? Make sense? Yeah, no, maybe. Right, and I'm sure, again, well, you would have covered a lot of this already, I guess. So where we are at now, so the analysis equation, so if we put it together now, the analysis equation, which is the complex exponential form of the Fourier series, it tells us what frequencies are present. So this is like a recipe here. This is telling you that the ingredients for a recipe, right? You all, whoever will learn to cook during the pandemic, so this is telling you that, okay, this particular thing has salt, black pepper, onions, tomatoes, beef, whatever it is. That's the analysis thing. So it's telling us what are the ingredients. The synthesis equation, which is the other part, and that is CK here, tells you how much of each. So this is the one, back to the same recipe. This is going to tell you a teaspoon of salt, right? A tablespoon of this, a half pound of that. So they both work together. One is telling you, okay, the analysis equation is telling you that we have frequency omega naught, 5 omega naught, 9 omega naught, right? And this now is telling us how much omega naught we have. So we have 0.5 omega naught, we have 0.75 of 5 omega naught, we have 10 of 9 omega naught, that kind of thing, right? So both of them work together. One tells us what frequencies are present, and the other one tells us the actual magnitude of those things. And if you put it all together now, then overall what you get allows you to build up the spectrum. So for any continuous time periodic signal, we could determine the frequency components that make it up, and the amplitudes are given by the CK values, and the frequencies are the multiples of the fundamental values, the fundamental frequency inside of there. Fair enough? Yeah, no, maybe. Right. So I have one yes, one maybe, and one fear. Yes, it is something that you're going to have to think about, right? So I'm stopping here today because I wanted to make the introduction before we actually do. There are some examples that we will start to look at, but I wanted to make sure that you understand what we're doing here. So you take any periodic signal. The Fourier series says that any periodic signal you could break up into a DC component and a sum of cosines and sines. There's a more compact form of the Fourier series. So instead of dealing with the trigonometric thing with sine this and cosine that, we can express the things in terms of the complex exponential form. And we know that e to the j omega t is cosine plus j sine. So we could go from one to the other back and forth as our heart desires. Having decided that we're going to use the more compact form, and the reason is that because the more compact form resembles something that we are already familiar with, which is the Laplace transform, then the Fourier series has two parts. One, the analysis equation, which is the sort of summary equation, if you like. So this one summarizes what the behavior of any periodic signal is. So it is going to tell us something in terms of the periodic signal's fundamental frequency. So it's going to tell us that the periodic signal has a C naught plus C1, what do you call it? K1 omega, omega naught T plus C5 K5 omega naught T, right? K, of course, going wherever it is, K1 will be 1, 2, 3, 4, or 5, whatever that happens to be. We're running from minus infinity to infinity. And then each of these now, the C1, the C2, and C3, we can work out how much it is by performing an integral. So we take the same signal and we integrate it. We multiply it by this thing that looks like the Laplace transform, except instead of S, we have jk omega naught t. So for each of these k's, so when k is let's just use the positive numbers for argument's sake, but we know it's positive or negative. So if k is equal to 2, then this now will be e to the minus 2 omega naught t. Right? And you will be integrating xt e to the minus 2 omega e to the minus j 2 omega naught t. And you integrate and you will get the value of C2 at that point. C5 will be e to the minus j5 omega naught t. And when you integrate, you see what the value of CK is. Right? Make sense? We're going to do a lot of examples of this, and then we will move on to the part where it starts to become continuous, which is what we call the Fourier transform part of it. Yeah? None? Or you're in shock? You're in shock? Or, okay, lightning. Yeah. All right, so at this point, I'll stop here today. So we did the work on the block diagrams, which I say is a cutoff point. We now want a new section of the course. This is not on a midterm, right? Which doesn't mean that you're not going to listen to it. Please do, right? And as we go forward, the next thing, when we meet next time, we're going to talk about, we're going to have an example here. So here's a square wave pulse. We don't know anything about T and T1 as yet. And we're going to apply the Fourier series to that and see what information that can give us about the signal. All right. And then after that, now we're going to move on from there and see what happens to the signal. Remember, the Fourier series only applies if the signal is continuous and periodic. So what happens if the signal is not periodic? And this is where the manipulation will start to take place, leading us into the Fourier transform. And that is even closer to the Laplace transform. And then everything that we were doing when we were talking about oscillators in the circuits class will start to make sense. Yeah. Okay. So this is it for today. Let me stop the recording.